Today we're super fortunate to have Peter Richtarik here with us, who is a professor at KAUST, who is also an absolute pioneer and leader in the space of federated and distributed optimization. So if you've done any work in the space, read papers on the topic, you've read at least one, if not many of Peter's papers. So I could not think of a more perfect person to give this tutorial. The tutorial today will be split into 3 parts. So we'll have 2 sessions this morning with a break in between, and then we'll have one in the afternoon. And then later this afternoon, we'll also be hearing a little bit about how federated optimization can also be used to train LLMs in data center environments. So thinking about the transfer of traditional techniques from federated optimization, going back now to data center distributed computing. With that, Peter, take it away.
Thanks a lot. So thank you for having me here. It's a great pleasure to be here. In fact, I've been to the very first program, Simon's program, in 2013. I was here for the whole semester with 2 of my PhD students. And since then, I haven't really attended beyond just a few workshops, not the whole semester. So those of you who are here for the whole time, hope you'll have a great time. So I will talk about federated optimization. This is going to be biased or even very biased tutorial. And the reason for that is there's way too much work that has been done over the years, and it's really impossible to cover it all or even roughly cover it all. It's just impossible. So I chose a few topics that I would cover in some depth, and some of them I would just glance over, and I hope we'll have some discussion as well. Feel free to interrupt me anytime. If many things that you know, maybe some things that you don't know, and we can talk about those things at more depth. So these are the 4 parts of the tutorial. First, I'll have some overview of some generic thoughts about the field and how I want to think about this tutorial. And I'll also include very brief discussion of some things that I will not talk about in those lectures 2, 3, and 4. And the major focus will be on communication compression, then on local training and device heterogeneity, these 3 areas. And I'll start from some basics in each case, really from the fundamentals, all the way to the latest things that we know and that we don't know in each case. So that's the plan. All right, so as I said, the field is way too broad. It's not possible to cover everything. And one can talk about the history, future of the field. I'm not going to do that. The future maybe there'll be some hints as I go through these other lectures and I get to the latest results. There'll be some questions there, but I will not really attempt to chart the history of this at all. Now, one can talk about the mathematical formulations of federated optimization of federated learning. There is no real consensus here. There may be kind of a semi-consensus of what you have seen before, this weighted average of these localhost functions and so on and so forth. But there's all kinds of other ways of thinking of federated learning, and the way I want to think of federated learning is much broader. And this, I think, it's very clear also from the recent shift in industry focus towards training large language models between data centers and so on. The way I want to think of federated learning is that it's distributed learning or distributed optimization in the wild, where everything that you might think is easy in some data center setup could be potentially difficult. Communication could be difficult, could be heterogeneous, could be unstable. Computation nodes could have different speeds or even the time-varying speeds. The communication topology could vary in time or could be static, could be one-to-all, could be this parameter server or hub-and-spokes model, could be anything. So I'm thinking of the computer architecture as being potentially anything, and you want to design an algorithm, distributed algorithm, or federated algorithm for that setup. And since these new applications of large language model training share some similarities with classical Federated learning. Many of these basic ideas of communication compression, local training, device heterogeneity, and so on, and the algorithmic tricks will apply there too. Right, so one can also talk about fine-tuning. We have seen a little bit of that yesterday. I will not really talk about it. I'll mention it on one slide, and then I'll move over. One can think of agnostic Federated learning as a different formulation of what Federated learning is. Again, I'm just citing it at one point. I will not talk about this. I will focus on this classical minimizing of the average of a bunch of functions approach, which is equivalent to the weighted average formulation. Now, another way I want to think about federated optimization is that we have to think about the computer that is going to be doing the optimization. And one has to fine-tune the algorithm to the computer. So if you have a parameter server architecture with this cross-silo, cross-device, or any other variation, there's certain bottlenecks. Maybe communication is expensive. Then you worry about communication, you don't worry about computations. Once you solve the communication bottleneck and computation becomes bottleneck, you have to worry about that one. Maybe then you realize the model is too large, you cannot store it on a single device, then you have to have model parallelism or something else, and so on. So all of these resources are there, and they may vary, may be heterogeneous. So I won't talk about these fully decentralized approaches where you work over a network, but potentially this could be at some point in the future of federated learning. I will not talk about, let's say, pipeline parallelism at all, or model parallelism. I'll mention this on a few slides, but all of these things are very, very important right now. We don't have very good way of modeling this mathematically. I have not really seen any papers on, let's say, good model of model parallelism, where one would see that an algorithm benefits from model parallelism. I have only seen type of research where you just bound away everything. You basically prove it will converge, but you will not benefit from knowing that you have model parallelism. So there's all kinds of other considerations, privacy, security, or federated X. We talk about federated analytics and so on and so forth. I won't be talking about those beyond maybe a few slides. What I want to focus is on algorithmic considerations and theory, the fundamentals, the stuff that carries over from architecture to architecture in some form or another. Okay, that's the focus. So I won't be necessarily focusing on these prevalent architectures right now, but the focus is towards these fundamental issues and so on. So we want to understand them in isolation. That's why I'm structuring the lectures in the way that I'm doing. We look at communication as a bottleneck, and we'll ignore all kinds of other bottlenecks for a while to understand what you can do if communication is the bottleneck. Obviously, communication being bottleneck is just a model of reality. In reality, once you solve that bottleneck, some other bottleneck pops up, and so on and so forth. But if we want to be able to understand fundamentally or mathematically how to design algorithms for these complicated computers, we have to first understand these ideas in isolation, these tricks in isolation. And once we do, or if we do, maybe in some cases we'll never do. Just like we don't really understand, we don't have a proof that a car works right now. It's an engineering construct. Everybody trusts cars, but we don't have a proof that it works. So at some point, mathematics doesn't apply. But we'd like to go as far as possible so that then the engineering can be built on as strong foundations as possible. And in some cases, we can see that these techniques do combine. They have added benefit, and this gives us increased confidence in these techniques. All right, so as I mentioned before, there are many possible mathematical formulations of federated learning. The two most common ones would be minimizing the average of finitely many functions, because you have only finitely many computers, even though when we think of cross-device federated learning, we don't really have infinitely many devices. So in some sense, it's just an approximation of modeling aspect. In reality, you have finitely many devices. So we don't lose anything by assuming that you have finitely many machines. And whether you minimize the weighted average or unweighted average doesn't matter. It's completely equivalent. You can just hide the weights in those functions, and then everything is just uniform average. Okay, so I will just simplify, abstract from them. I'll assume we'll be just minimizing the average of functions. And I won't talk about some other formulations, such as agnostic FL. I'm just throwing in here this citation. So here, this is interesting work, and there are many other different formulations where you want to say, you don't want to minimize the uniform average over loss functions, but the worst case average, because you don't really want to trust that this is really the goal of the training in machine learning. There's like reasons, and if you look into the paper, they argue very well, these authors, why that might be the case. I will talk a little bit about personalized formulations or this fixed point formulation and so on, just to highlight on a few slides that there's a world beyond this finite sum minimization problem. But this will be the main formulation I'll work with. And even though it's surprisingly simple looking, there is a lot that we still don't know about this on a fundamental level. So here, lowercase n will be the number of machines or workers or clients. Many authors use capital M. I just use n here. And this would be the loss on client I. Could be expectation over some distribution. Could be just you have a loss. You abstract from the fact that you have some distribution. And you'd like to find a model which minimizes the average loss. And again, this is completely equivalent to the weighted average formulation. Now, the kinds of algorithmic considerations you have to take into account when solving this problem include all of this and more. So for instance, you can think about server extrapolation. There's some beautiful works on this. Once you combine all of updates from different workers, what do you do with those updates? Do you just do simple averaging, or should you extrapolate, or do something else? Should you have a server optimizer, and so on and so forth? So again, I will have just a couple slides on this. The major focus will not be on this at all. You can think about server aggregation, partial participation, all kinds of other things, and I just don't have the space and time to talk about all of these things, so I just chose these three: local training, compression, device heterogeneity. Okay, so here are some philosophical thoughts about approaches to FL research. So most papers, and I'm just making up these statistics, this is not, I didn't count anything, okay? But I would say from my own personal bias observation, most papers are empirical. They don't contain any theory. And this is completely fine. Okay, I'm not judging any of these approaches to research. Everybody, there's a variety of research. There's a wilderness of approaches to research, and this is good. I'm just stating my observations here. Most papers are empirical, and the way they work is they focus on stuff that is useful in practice. You build a system, you solve some application problem with this. Hopefully, this is useful to someone, and if it works, and maybe you don't know why, but it works, and that's fine. However, since you don't know why, things may get complicated at some point, and when we're seeing a lot of this already. So it may be very difficult to operate such a system because there's lots of bells and whistles that you have to fine-tune. You have to decide all kinds of parameters, and you decide this a little bit wrong, and everything collapses. So you can have a very brittle system that is not robust at all, and it may just not work at some point. And the process works in such a way that you start with something that works, and you keep making more and more complicated, adding some features, always only those that hopefully help. So some sort of a trial and error. Of course, you have intuitions from lots of experimentation, maybe from theory, but ultimately, you don't really have a proof that this whole thing that you have works. Or maybe you do, but you may not have any efficiency guarantees at all. You just know that, okay, maybe it works, but it can be very slow. Now, if you look at the theoretical papers, I would say that most of them, again, 99% of them, they try to understand on a theoretical level something that doesn't matter that much. So either you bound a number of iterations or round of communications or some sort of a very, very rough estimate of efficiency, which may not be what you really care about, because that estimate may be very, very far off from a real kind of cost in practice. So for instance, if you count the number of communication rounds, but each communication round varies just because you have heterogeneous clients that are available, not available, and so on, or do more or less work, then this doesn't make all that much sense. Okay, so this leads us to this idea of a cost model, which I don't,
Yeah, maybe there's not a clear answer to this.
Yeah.
But in your opinion, like, what should theoretical papers be counting?
This, okay. So I'll talk about it right now. So cost model is some sort of a model of the total training time. So let's say the total training time is what matters. You may question even this. It may be the cost of the training process or whatever, but let's say training time is what matters. Well, if you count the number of iterations, this is not a good idea. Okay, and you'll see this later on why, but you can already believe the number of iterations doesn't really, for parallel methods, distributed methods, doesn't really correspond well to training time. It's kind of good as a proof of correctness, because you count the number of iterations, so you know that eventually at least you have a method that will solve this thing. It's not a heuristic, but how the number of iterations really maps onto the training time, that's just very unclear. But most papers focus on this kind of a thing. Now, the cost model should really be informed by the computer that we're using to solve the problem. So if you have the classical architecture, which would be just hub and spokes, just this part here, right? Then you may say that, okay, this communication is what is expensive, so I will just completely disregard cost of aggregation. I will completely disregard cost of computation, and I will only round the number of count the number of communications. And then that is a good proxy for training time. But as soon as you have this kind of a hierarchical model, and this is something that we have proposed in some papers several years ago, where maybe this is your house, say, and these are all the devices in your house. This is somebody else's house, all the devices in that house. And this is some kind of a city-wide aggregator. And you can go and aggregate further and further, then maybe this communication is very fast and this is slow, say. And then a better model for time would have to take into account the fact that this is much slower than this. Well, maybe this is much faster than this. Things can be, yeah.
What do you mean by iterations? Like what is iterations in this model?
This is just this is not in this model. Whatever is the algorithm, you count the number of iterations. You just, whatever is the natural way of counting iterations
But the
in an algorithm.
natural way might vary if it's a hierarchical algorithm in your model.
Exactly, and that's my point, that we should have a cost model which reflects this, and then you would not really be counting iterations, you're counting something else. That's my point. So here to be more concrete, let's look at setup where what matters is where you have a setup where you have just one computer here, one hub, and some spokes. And the uplink communication is very slow, and downlink communication is very fast. Okay? And everything else is fast. There's lots of memory everywhere. There's super fast computers. The compute time everywhere you can ignore. Let's say you have this kind of a setup. Then you may want to be counting number of rounds multiplied by number of bits pushed to the server or to the hub. And you don't count any compute, any aggregation time, nothing else. Okay, so this is a little bit maybe better model than just counting number of rounds. Why? Because if you count the number of rounds, you may be disregarding how much that run takes. And this depends on whether you send full dimensional messages or whether you compress messages and so on. So it matters how much you communicate, right? Because if you communicate very little, you can take many more rounds. So number of rounds will not matter, right? If you want to compare different algorithms. Or maybe you realize that, okay, I cannot quite ignore the downlink communication because maybe it's just 10 times or 100 times faster, but not infinitely times faster. So you will have some constants, A times up bits, B times down bits, and some kind of parameters, A and B. And depending on what that A and B is, you may be using different version of the same algorithm, okay, which may compress or not compress more or less one or the other direction. And maybe you now have an algorithm where all of this is really good, and then you realize that the bottleneck is now the compute on these devices, the local training. You cannot ignore it anymore. And most papers, in fact, all of that I've seen, until we wrote this paper, did ignore that compute. Why? Because even this was not understood, how to optimize over this. So why would we complicate with this if we don't even understand this? So you would add compute time with some scalar. So now we have a little bit better cost model. But all of these are toys. All of these are models. They're not perfect. Okay? And you can keep complicating this, right? So once you start working with memory parallelism and pipeline and whatnot, things just become more and more and more complicated. But we do already have answers to some of these questions, even for these more complicated models. For some of them, even we know what are the optimal algorithms in some settings. And granted, these are toy settings, not the settings that we use in industrial practice. So this is the work where we're able to show that when you have this kind of a model, this last one, then we know that, for instance, when you choose a local solver, it should not be simple SGD, but it should be variance reduced SGD, because that makes this whole sum, this whole total cost smaller than if it's just SGD or GD. Okay? And we should compress communication, not compress communication, and so on. You should do local training and not do local training. So these design decisions will be made for you once you have the right cost model. Okay? Yeah.
What are the units of A, B, and C? Is it seconds per bit or something else?
No, these are just numbers, and they will be whatever. You have a computer, and you measure what costs what, and you choose these units, and these A, B's, and C, so that this is time. So that this is comparable to this, and this is comparable to this. So when you add things up, this actually is going to correspond to time. That's all. I mean, we don't need 3. We can just divide by A and have just these 2, right? But I just chose 3. Right? All right. So of course, constructing such a cost model is super complicated, and it's complicated because many things. One of them is this computer architecture. Once you start looking inside here and just start thinking about cache and start thinking about communication inside between the GPUs on that device, you can start modeling that. Then things will just become more and more complex and more accurate, but more and more intractable from a mathematical point of view. But there's additional complication that is just heterogeneity of everything. And by heterogeneity of everything, I mean you can have data heterogeneity, compute heterogeneity. What if this device is 100 times faster than this? Or what if these are 3 data centers, and this is some kind of hub, but this data center is 100 times smaller than this? We still want to train a model, maybe a large language model with these 3 data centers, but this one is 100 times smaller, or right? Or this link is much faster than this link. So you have this heterogeneity. And you can have heterogeneity in time as well. Right? You can have some links just get saturated over time, and then some other day they are not, and so on and so forth. You can have model heterogeneity because of memory heterogeneity, and so on and so forth. So things can get more and more complicated, and we don't know much about this. Okay, so here are some further thoughts on how I think of understanding of algorithmic tricks in the literature on federated optimization. So when you look at the papers in federated learning, federated optimization, many of them would have some algorithmic tricks, such as local training. So you think of federated averaging. What is federated averaging? Combination of 3 tricks. First of them is partial participation. Not all clients participate, but only some subset. Second trick is those that participate don't work with all the data that they have, but they do a stochastic approximation. They use stochastic steps rather than deterministic steps, the second trick. And the third trick, they don't do just one step, but many local steps. You combine these 3 tricks, you get federated averaging. Now, these are 3 tricks. Do we understand them? Well, it took the community time to understand them in isolation. And when you look at one of these tricks, so let's say local training, which is the most complicated of them, then for a very long time, the best we could say is that this has negative effect on the algorithm. You introduce the trick, you get a worse method. The mathematics says you shouldn't do it. So you get a bound, so you get a valid algorithm, but if the bound is to be useful in telling you whether you should use the algorithm or not, the bound just gets worse. Don't use it. Don't use that trick. And then it took some effort for the community to reduce the effect to smaller negative effect, and then maybe no negative effect at all. So some work of Sebastian, say, right, in this case. And then it took time to figure out that, in fact, it could have positive effect, and then we understood that local training trick. And only then you can start thinking of it in combination with these other tricks. And these are just 3 tricks, and there are many, many more tricks. There's error feedback and all kinds of other tricks. So I want you to consider thinking about algorithmic tricks from this perspective. So ideally, and in this tutorial, I want to think of these tricks as something that should provably improve the algorithm. It should be something not there just so that it's there. We want it to help. And then when you look at theoretical bounds in the literature, there's this hierarchy of these bounds. Of course, you don't want to be here. And very often when I review, or I review very little these days because I do ACs and these kinds of things, but when I do review, the first thing that I do, I start looking at the proofs, because probably 50% of the time I find a mistake in some proof. And then I can reject the paper. Okay, so I don't want to do this, but I found by experimentation that this is what you often find. So you don't want to be here. And then when the proofs are correct, typically you get some bounds which you shouldn't trust. So the bounds exist and basically just tells you the algorithm is not a heuristic, but doesn't mean it's a good algorithm. Then you have some reasonable bounds or bounds with predictive power. Those are really good ones. Or you have bounds which are not improvable optimal bounds. OK, so there's a bunch of topics I will not really talk about in these lectures 2, 3, and 4, just in this overview. But I'll talk about them at least very little bit so that I don't skip them completely. So first is client sampling. I will really not talk about it, but I mentioned a few papers. So I said this is biased. This is our paper from some time ago, where we look at optimal client sampling. What you can try to achieve is to achieve the same performance with a subset of clients as if all the clients were involved. And in some cases, this is possible with this type of sampling that was proposed in this paper. So this is a different work with a unified analysis of all kinds of arbitrary client participation. This is kind of work where you say almost anything can happen. Not anything, because if you allowed any kind of pattern of participation, then you get a heuristic and you get a method where you can find a counterexample and just breaks down. So you have to have some regularity, but this paper is trying to involve as broad an array of possible participation patterns so that you still have some convergence guarantees. Okay, so there's that kind of work. And in this work, there's a certain type of participation which provably improves the system. This comes some sort of double reshuffling of clients and the data on the clients. I will not really go into the details, but in this case, the bound is rough, but it involves lots of participation patterns. This is only one particular participation pattern, but this one probably helps, and that one also helps. OK, so some new topics in Federated optimization, Federated fine-tuning. So this is some work from our lab and collaboration with a London lab with Samsung AI. So here we looked at LoRa as an optimizer, and we realized that there were no papers with any theory. All of this work has been driven by empirical success, and that's great. We wanted to have some understanding of this, and we realized we found a 9-dimensional counterexample where LoRa or chain of LoRa, it just fails. It's a heuristic. So we have industrial success with LoRa-type methods, but but we're lucky in some sense. So here, everything fails. And the method that we suggest, which is some sort of modification LoRa, which we call randomized asymmetric chain of LoRa, works well on that 9-dimensional example. So this is not any industrial scale. This is tiny, tiny counterexample. But here's a fix. There's some beautiful work by Gowrie and Cotters, and here's some symmetrized version of this RAC LoRa. There's been a lot of work on outer solvers, or the server solvers. The latest one is by Ahmed Khaled and Cotters. So this would be the one that I would recommend to everybody maybe as a starting point, because this is the latest one, which builds on all of these other works and cites them and explains how these developments fit into the literature. So for instance, this is the first understanding in this paper of an accelerated outer optimizer, such as using Nesterov momentum, as used in diLoco. And the effect of momentum is understood. There's also some high probability analysis, which maybe is less important compared to the momentum and outer optimizer analysis. To the best of my knowledge, the first proof of an extrapolation benefit, theoretical one, was provided in this Nastya paper. This was later superseded by this FedEx prox understanding, and here's the latest understanding. So again, beyond this one slide, I'm not going to talk about server optimizers at all, but I want you to be aware that this thing exists, and if you're interested into this, you can read these papers and try to think about this. So here is a couple of slides on different formulations of federated optimization. So I told you we'll be working with this finite sum minimization, but here there's a different formulation. So let's think about this one, for instance. So here you have average of FIs of XIs, so you allow every single client to train their own model. These models can be different. And then you have a penalty where you penalize by the variance of these models in the parameter space. You take xi minus the average of xi, square this. So what does this mean? If the penalty is very large, then this tends to the classical formulation, because then all the xi's must be the same, right? If lambda is 0, then this is not even fair learning. This is completely embarrassingly parallel or distributed optimization, because everybody just trains their own model. No communication has to happen. So now you can already see from the formulation alone that depending on the parameter of lambda, if you run a good algorithm to solve this formulation, if lambda is smaller, the problem should be easier from the point of view of communication complexity, right? Because if lambda is 0, no communication is needed. And this is in fact the case. In this paper, we show that the expected number of communication rounds is basically lambda times something. So if lambda is small, it's small. Now, that is not that interesting as the following observation, that the very natural algorithm for this formulation is the following. Think of this as a two-sum optimization problem, where the first function is this average of FIs, XIs, and the second function is this penalty. And try to run SGD for this two-sum problem. What would stochastic gradient look like for the first function? That's one step of local training, right? And what would one SGD step with respect to the penalty mean? It's a step towards averaging. It's not full averaging, but the step towards averaging, okay? Which is the classical aggregation strategy in federated optimization. So if you do SGD, but now with non-uniform probabilities, with much higher probability you pick this than this, then you get a method which looks just like local SGD. It's not exactly local SGD, but it's different only in two minor ways. So you take step towards averaging, and you have some sort of random number of local steps. And from this, you can already feel that local SGD probably is going to be super, super interesting method if lambda is small, because then you get very small communication complexity. And you can think of this as some sort of a hand-waving type of a proof that if you run local SGD, you're really solving this problem, not the original problem. Because I told you that the SGD of this type for this problem is something that looks just like local SGD. Okay, so here this is a different point of view of how to think of communication complexity combined with personalization. for this formulation. And of course, this is a personalization because you allow, by the choice of lambda, different types of models, so personalized models. Okay, so then in this work, the authors provided optimal algorithms for this formulation. Here, this was all generalized to partial personalization. Here's different formulation with the same theoretical properties where you don't have to do any local training at all because you just pre-solve. Everybody does their own training before you start doing anything. So everybody finds argmin of FIs and then solves something different. You get the same effect. And so on and so forth. So I will skip this. Maybe I'll just show you on one slide this Flix idea, which is an alternative to this. So think of this formulation of federated learning, very different, federated optimization. Not a classical one at all. You want to minimize the average of FIs, but now you have a convex combination, and these alphas could have subscript I. I just, for simplicity, chose alpha, okay? Convex combination of a trainable model X and xi star, where xi star is the optimum model for client I based on their data. So they can pre-train on their own data. So now, if alpha is 1, this is standard federated learning, right? If alpha is 0, this is what? This is don't communicate at all. Everybody just solve your problem on your own, right? So if you think about it, this has exactly the same feel as this, except we have a different parameterization path between the same endpoints. One endpoint is everybody trains on their own, no communication is necessary. The other endpoint is minimize the average. Here the interpolation is the function loss space. Here the interpolation is in the parameter weight space. But the good algorithms for this don't have to involve any local training. Why? Intuitively, because all the local training that was necessary for the acceleration was done at the beginning before the algorithm, before we even formulated the problem. It's all hidden here. So once you pre-train with this, you don't need local training anymore. And you can just jump at this formulation, and you can use any standard solver right away. Yes?
So I had one question going
Yes.
back to the initial
Yeah.
formulation
Yeah.
that you used. So if we look at the arbitrarily heterogeneous setting where the clients don't have any assumptions on how their data distributions
Right.
are related,
Right.
then first of all, it's not clear to me why are we even solving that average problem? Like if the mathematical problem cannot even
You're
match-
absolutely right, and I'm not at all claiming that.
So then
Yeah.
here's my second question.
Yes.
So if I don't assume anything
Yes.
related about the clients,
Yes.
then shouldn't having xi star sort of solve the problem in the first place? If it doesn't, then I should assume something related.
No, you're right. We can criticize this, and we can criticize the original one. We can criticize all of these formulations, and your criticism is completely valid. And I don't really have an answer of the type, everything is right, you're missing something. You're not missing anything. You see through it.
So my question,
But my answer here would not be mathematical, but would be empirical. And the answer would be, solve this problem for varying alphas, and look at some sort of generalization. Here is recall. And you would see that recall is better for something in between those two extreme points, 0 and 1, which tells you that this parameterization is useful, that it is better to personalize in some sense. It is better for not to solve the original formulation, which would be this one, not to solve everybody trains on their own, but do something in between. Can you do even better? Maybe yes, with a different formulation. But I don't have any mathematical answer to this. This is purely empirical.
okay, I completely agree.
Yes.
My question then
Yes.
is, doesn't this suggest that we need a better theoretical model to study
Yes,
the question?
yes. Yeah. So for instance, this agnostic FL is one attempt at doing this, and there's some others, but I'm just not covering them in this tutorial. But yes, we need to even revisit the foundations. So here I'm just assuming that we want to minimize the average of FIs, but maybe those are not the FIs that everybody thinks they should be. Maybe there should be different FIs, and everything I'm going to say applies to that setup, whatever the FIs are. Might not be the FIs that we think, that this is just the losses of those.
But my problem
Yes.
is like even the best thing that you could prove
Yeah.
in this model, what does this tell you? Like empirically I understand
You're completely right.
empirically I understand it can
Yeah.
lead to better algorithms. I'm completely on
Yeah.
board with that.
Yeah.
But theoretically, what does this exercise give you? Like if you study this model.
I don't have any theory for this. So there's no, for this one, no.
No, not just
All I'm
this one,
saying,
but in-
I'm with you. I'm with you. I'm trying to precisely make your point. And the point is, there are multiple different formulations right now. None of them is really the right one. We don't know what the right one should be, but all of them are in some sense useful. Okay? And we need to revisit that also. I'm not going to give an answer to this. Okay? Yeah. Okay. So, Byzantine workers, yet another thing that is often overlooked. So maybe some of these workers will not want to collaborate. They will not send you gradients or local updates, but they will send you just some messages that an attempt to destroy the training process. So the Byzantine worker with a worker which doesn't want to cooperate, wants to maliciously harm the system. I'm not going to give formal definition, very, very informal. So here's a beautiful paper by Martin Yagi and co-authors, where they noticed that prior robust aggregation rules don't really work mathematically, and they suggest some fixes with some clipping and momentum. In this work, we noticed that variance reduction actually proves is a provable technique for improving the behavior of algorithms in presence of Byzantine workers. So without these techniques which we introduce here, you get stuck. With these techniques, with this technique, you don't get stuck, okay? And so on and so forth. Again, just one slide. I'm not going to talk about the Byzantine workers at all, but one can have a whole lecture about Byzantine robustness. Model heterogeneity, again, just one slide. What if you have devices? Each of them has different memory footprint. So one can store an entire network. The other one can store something much smaller. Another one even much smaller. What can you do in that setup? Not much is known. Here are just some two of a bunch of papers, but not so many papers on this topic. Okay, I'm not going to really talk about what's going on here. There's work on objective inconsistency. So what is the idea here? The idea is, what if a client does a lot of local training rounds to minimize their own function Fi? And we'll talk about local training later on in detail. But each client takes a different number of local training rounds. So somebody progresses towards minimizing Fi a lot, somebody just a little. Maybe you shouldn't be averaging those models. Maybe that gives some kind of a bias, and you come up with an algorithm which doesn't provably converge to the minimizer of the average. So here, this problem is tackled through some weighted averaging technique. There's some other topics having to do with privacy, analytics, application systems, and so on. Maybe I would highlight this one recent work where we achieved DP guarantees without strong optimization assumptions. Typically, you have these strong assumptions, and it took community time to figure out how to get rid of them, and some other notable papers. Okay, so now would be the time to move. I have what? Okay, 15 minutes to start this lecture two. Any questions about this overview? So this was very rough. It was supposed to be rough. If some of it was not understood, it's okay, because I told you I'm not covering any of this, what I kind of covered. It was supposed to be superficial. Okay, so this should just give you an idea that there's all kinds of stuff out there, which is interesting, but we're not going to be covering, okay? So if you don't understand it, it's because I didn't cover it, okay? Any questions? All good? Am I going too slow? Who thinks I'm going too slow? Too fast? All good? Okay. Who doesn't care at all? Okay. All right. So communication compression. So we'll work with this formulation. It's exactly the same slide. That's why it looks the same. I copy-pasted it. So the idea is we'll use the following cost model. I want you to be aware of these cost models now. And as I say, in papers you will not find them. People don't talk about them. It's all implicit. So the cost model is that nothing costs at all except for the communication from the client to the server. Everything else is for free. Of course, this is just a model. It's not true in reality, but let's say that's the bottleneck. So we care about it first order of approximation, that's That's true. What can we do in this situation? Well, one thing that we can do, that we was suggested in the literature some time ago, these are probably not the first papers. I didn't really try to trace it all the way back, but these are some of the first papers that I'm aware of. QSGD by Danali Starr and Cotters, and this DCGD by Sarit Kiriradan Cotters. Sarit is now postdoc in my lab. So it's this very simple algorithm. So how many of you have seen this before? I just want to just understand who I'm talking to. Okay, roughly half. Good. This is excellent. So the idea is this. Take an SGD type step. Okay, this is model, learning rate, stochastic gradient. What is the stochastic gradient? Is the average, not of the true gradients. If this was the average of the true gradients and this operator was identity, then GK would be the gradient of F, right? Because the average of gradients is the gradient of the average, right? So once you modify these local gradients, which are computed locally, with some compression operator, and this be lossy compression operator, and I'll give you some examples very soon, okay? Lossy compression operator, then this will become stochastic gradient because these operators would be randomized. And if they're not randomized, then it would be some kind of inexact gradient, okay? Some kind of rough gradient. The idea is this is difficult to communicate because it's a huge d-dimensional vector of, let's say, 32 or 16 or whatever bits. And this might be 100 times or 1,000 times smaller. So be 100 times or 1,000 times faster to communicate. Okay, that's the idea. So that's DCGD, distributed compressed gradient descent. Now, there's a whole bunch of compression operators that were suggested in the literature. The most common is this class of independent, unbiased compressors with conic variance. I give you definition soon. And some examples of this is natural quantization, or randomized low-rank approximation, or scaled sparsification, and so on and so forth. So then there's this larger class of biased contractive compressors, where examples are, let's say, top K compressor. The idea is that you have a vector, you take the absolute values of all the entries of the vector, and you keep only the top K values in magnitude. That's top K. Round K would be you take random subset of those values of the gradient. Now here's an even larger class which generalizes these two, which is this BV class, which we came up with several years ago. The idea was to get deeper understanding of what's really going on. Why do we need deeper understanding? Because the algorithms that deal with these compressors have very different theory from the algorithms that deal with these compressors. Okay? Once you work with these compressors, these biased contractive compressors, DCGD diverges. There are counterexamples. It may just fail, even exponentially diverge. Very often in my work, but you can come up with counterexamples, it can diverge. You need some fix. But here, this doesn't happen. Divergence doesn't happen. You get some kind of convergence to a neighborhood. And you can fix it with some mechanisms, variance reduction mechanisms. So the idea is to what's going on. Here's an interesting class proposed by Slendang and Cotters, these AB compressors. The idea is use unbiased compressors, but make them correlated across the workers, right? Because the idea is, well, we want to save on communication, so we want this to be as accurate approximation of the full gradient as possible. So maybe these workers that do the compression should collaborate to figure out how to compress rather than do the compression independently in order to come up with a more faithful approximation. And the question is, can you do that in such a way that you get mathematical benefit? Not just practical benefit, but also mathematical benefit. And the answer is yes. If you work with these compressors, these AB compressors, and in particular the permutation K compressor, you get mathematical benefit. And in practice, it's much faster, of course, as well. Then you can come up with compressors which take the data into consideration. And then you can get further mathematical benefit. You can have some other classes which are not subsets of these, let's say randomized integer rounding. I'll show you what I mean by this later on. These are not all the classes, but these are some of the major classes out there. Okay, so if you want to find the definitions of these things, I'll give you a few examples, but if you want to find the definitions, I color-coded these papers. Okay, so these are the unbiased, these are the whatever, Okay, you have the colors there. Okay, I will not be going through this. And in some of these papers, you have these tables of multiple compressors and their properties and so on and so forth. So if you're new to this area, you can just easily get into it by looking at these papers. Okay, so I give you some examples of sparsification and quantization. What's the idea of sparsification? The idea is you don't send the full gradient of D floats, but you send a subset of the floats. And you have to choose how the subset is selected. Could be randomized, could be greedy selection. Quantization is you send all of the floats, but they will not be 32 bits, but maybe just 4 bits or 16 bits or something like that. Okay, that's the idea. And you can combine them. And there's theory telling you if you combine them, you still sit within those classes or maybe move to another class or something of that type. So here is an example of rand K sparsification. So let's choose this 5-dimensional vector. And we do rand1 sparsification, so we want to throw out everything except for one entry. How do we choose the entry? We choose it randomly. Okay, we don't even have to look at these numbers. So we flip a coin with probably 1, 5, we choose this entry, 1, 5, this entry, and so on. And we multiply by 5 in order to maintain unbiasedness. It turns out that these properties will be satisfied. So this will be an unbiased estimator of that vector. Expectation of the compressed vector V is V because of this multiple 5 and this randomness. And the variance of the compressed vector is upper bounded by a constant times square norm of the uncompressed vector. So this is something that we can call conic variance because the variance bounds is the same on the sphere, okay, of equal radius vectors V. So in some sense, this is conic behavior. Okay, so here, another instantiation of the same operator, another one, depending on how you flip the coin. So top case sparsification chooses always the entry largest in magnitude. So in this case, it would be -7. There's no multiplication by 5. And then you have a different property. First of all, you don't have any unbiasedness, obviously. So you lose a mathematical property. You lose a tool in proving convergence, let's say. And you get this other property. That this variance-looking quantity, which is not variance because this may not even be random, is upper bounded also in a similar way, but now the scalar is between 0 and 1. Okay? So this is, these are contractive compressors. In this case, with K is 1, you choose the largest one. If K is 2, the largest 2 in magnitude. If K is 3, the largest 3 in magnitude. Okay? Okay, so here is natural quantization. This is something that we proposed in this paper. And the idea is this. Do randomized rounding to the nearest power of 2. Okay, and this sounds strange, but it has very nice mathematical properties and also practical properties. So let's say you want to round just scalar minus 2.75. Then this lives in this interval -4 and -2. Those are powers of 2. And you round to -4 with some probability, -2 to some other probability so that it's still unbiased. Okay, you choose the probability so that expectation is -2.75. And you do this for every entry independently of the gradient that you want to compress, or of the vector that you want to compress. Now what happens here? Well, between this -1 and 1, you also have powers of 2, but they're negative powers of 2. So let's zoom in on this. So now you have -1, 1, and then you have other powers of 2, 1/2, 1/4, 1/8, and so on. So if you want to do this randomized rounding of number 0.6, let's say, it lives in this interval 1/2 and 1. That's how you do the rounding. Okay, so this is natural quantization or natural compression. Now, before this paper, quantization in the literature, where there was some mathematics for it, was done in such a way that you would have uniform subdivision or arithmetic subdivision of this interval, not geometric. And then the mathematical effect of the geometric subdivision is that you have exponentially less memory or exponentially small variance. So this is a really huge effect. Just small idea, really huge effect on the theory. And when you run experiments, you will see that if you use the right algorithms. Okay? So why do we call it natural? Because if you take, let's say, this binary 32 floating point format of a number, then it looks like this. You have 1 bit for the sign, you have 8 bits for the exponent, and 23 bits for the mantissa. If you just think about how to round this number to a power of 2, to the first degree of approximation, just deleting the mantissa. I mean, if you delete the mantissa, you round it up, down to the left deterministically to 1 power of 2. If you want to have this unbiased thing, you have to do something slightly more complicated, right? But it's almost as easy as just getting rid of mantissa. So it really, what you do, you go from 32 bits to just 7 plus 1 bits to 8 bits. So that's what you save. And when you plug this into some kind of theoretical analysis, you will actually see you provably gain. It's better to compress than not to compress. It's not that you pay for compressing, you gain. And the way I'm thinking of it, and I'll show you these theorems, the way I'm thinking of it is this. Even now, we communicated through compressed communication, because that's what language is. I'm not unloading the content of my mind onto you. I speak in words, and you decompress them in your minds. So human language evolved to be compressed, because it's more efficient that way. And it's the same thing happens in algorithms. Whenever you have algorithms where communication has to happen, compressed communication should be better than uncompressed communication. And this is one example of that, where it's going to be better, provably. OK, so here is natural quantization applied to a vector. You apply it to every entry individually, right? 4 minus 2, whatever. So let's say that these are the powers of 2. And one can show that this belongs to this class of unbiased independent compressors. And this omega I is very small, it's just 1 over 8. OK. All right. So now let's look at the DCGD theory. And I have, what, 2 minutes? And then we have break? OK. DCGD theory for this class, independent unbiased compressors with conic variance. What happens? So this is what happens. And I do this for functions which are L-smooth, mu strongly convex. And if you say, I don't believe that my function is L-smooth, mu strongly convex, then there's some other theorems which will give you some other results, but they'll only show you one. You have similar results without strong convexity and for non-convex problems as well, but they'll be, of course, weaker. But I want to show you the strongest possible insight that we can get on this simple model. So Li would be the smoothness constant of function Fi stored on client I. Okay? Omega I is what you saw. And this is why it matters. It shows directly in the iteration complexity analysis. And now I'm counting number of iterations. I told you I shouldn't, right? If we take at least this many iterations, then we have solved the problem. Okay, that's what this says. But number of iterations doesn't matter, right? Why? Because if we compress a lot, then we can take many more iterations in the same amount of time. If we don't compress at all, then we have to take fewer iterations, right? So we have to multiply the number of iterations by the number of bits that we communicate from the client to the server under our cost model, because that's the only thing that matters. Everything else is free, okay? So this particular analysis is kind of, you can deduce it from this paper, but it's not actually included in the paper, and I have it in my lecture notes. So let's now look at the number of iterations of gradient descent multiplied by d, because you have to communicate d floats. So that's the communication complexity of GD. Communication complexity of DCGD is this. I'm just plugging into the theorem. And this is for the rand1 sparsifier, where we throw out everything except for one entry. It turns out this is the best sparsifier. If you optimize communication complexity of DCGD over all rand k sparsifiers, you should use rand1 sparsifiers. Okay? This is not very well known, but it's true. And it's kind of simple exercise. So in that case, omega I will be d minus 1. And we want to see, is this number larger or this number larger, right? Because this is now the cost. This is the time it will take on this kind of artificial machine to solve the problem. So we take this ratio, and if this ratio is bigger than 1, that means we should compress, right? What is the ratio? The ratio is exactly this. Now, it turns out that L max divided by L has to be between 1 and n. That's just a mathematical inequality. It has to be between those. There's not an assumption. It has to be between these two endpoints. So this ratio has to be between 1 and this fraction, which means it has to be larger than 1. This tells you you should compress. By compressing, you can never lose. And you can gain as much as this fraction. Think about what this fraction is. If you go with d to infinity, right, then it's basically n. And if you go with n to infinity, it's d. So if you have a large model and fixed number of machines, then you can gain factor of n. If you have fixed model and many, many machines, then you can gain factor of d. These are huge factors because we work with the really huge d's and really huge n's, right? But if you work with just 10 machines, okay, it's not going to be larger than 10. Okay. Any questions? I want to stop here. First theoretical result we're talking about? Yes. Yes.
So when you implement the GD on the computer, you're using some default floating point operation, which is in your optimization library.
Yeah.
Do you still get D, or it is some function of D?
So I'm using floating point of the representation of the vector itself already? That's what you mean?
Yeah.
No, I'm assuming infinite precision memory. So I actually assume, because once you start thinking that you don't even have these vectors and these gradients in memory in infinite precision, then you just don't know what is there. There's already error there, and the analysis of this algorithm doesn't account for that error. So I'm assuming that the gradient is in full precision. These are reals. That means infinite, you need infinite memory, right? But then you compress, and that's what you send. You see? That's what I do.
I see, but
Again, that's a model. It's not reality.
right on the right, though, we don't, of course, make this assumption. You do account for the bias that is coming from the compression.
Yes,
Okay.
yes. For the
On the
compression.
left, I'm
Yes,
saying
yes. On
there's
whatever I'm compressing, I'm assuming I have it exactly.
Yeah.
That's the gradient in infinite precision. But then when I compress, I throw out everything, and it's D-to-1 compression. It's very lossy compression.
Yeah, all I'm saying is the green baseline. So
Yeah.
there's some trade-off between the error that comes from compression and the number of bits you need to communicate per round. And that is on one end of that spectrum, that green baseline.
Yeah.
In practice, you're somewhere in between.
Yeah, so this, you see, I'm assuming here that now every entry, in order for this to actually,
No, I understood what you're
Yeah,
doing.
yeah,
I'm
yeah.
just saying you're somewhere in between.
yeah, I'm somewhere in between.
So I'm trying
Yes,
to understand
yes.
what, like in a naive even like floating point, whatever I'm implementing,
Yes.
what is actually the...
So, okay, so let's say that everything is 32 bits. Then this D should be 32 times D, right? And let's assume that if you run the algorithm 32 bits precision, then the mathematics is correct, which is not true, of course. You would have to have analysis which accounts for it, but assume that the mathematics would go through with that error. Then this is analysis on top of it, because I do additional error through compression. So this is also a model. I'm not accounting for the fact that everything is stored inexactly on a computer. And no algorithm, almost no optimization or machine learning algorithms ever analyze that way. Everybody assumes these vectors are there as real numbers, right? They're not quantized. Nobody does it that way. So I'm not doing that either. Okay? Does it make sense?
Yeah.
There was another question somewhere? Yes.
Yes, I know you weren't analyzing round complexity
yeah,
with this, but like, how is the number of rounds affected by this quantization step?
Yeah, so this is the number of rounds. This is the number of rounds. This, exactly. Because in every round, I send only one float, so I multiply this by 1. Here, this is the number of rounds without the D, and in each round, I send the D floats, because I don't compress. So this is the number of rounds for DCD, and this is number of rounds times D for gradient descent. And I'm comparing the two things that should be compared, which is the communication complexity in my KAUST model. Okay? So this shows us that you should always compress, right? And the effect is huge. It's humongous, right? It could be this huge, really huge. So that is great. Now, of course, we have to take break, right?
You can go for a couple more minutes. It's okay.
Okay. So do you want to take break, or we do like 5 more minutes to 45? You choose. So we continue to 45 then, and then we take break. Yes?
I just had a question. I was curious. Has anybody looked at compression scheduling? So a notion of like, maybe early on you can make a lot of progress with a higher compression ratio. and then
There are
gradually
papers
less.
like this. None of them shows any benefit of that, in theory. In practice, it might be true. That just means we don't quite understand how to think about it theoretically.
Yeah.
But in theory, no. Even I've written some papers on some kind of compressors that evolve in time and so on. But those papers belong to the category bind the effect away. But I don't prove that it's better than doing it differently. Okay. So now, I want you to think about this in two different ways. So one way is that either we're working with this KAUST model, which I mentioned. Well, it's too far. I'm not going there. With this KAUST model, where you communicate to the server, and that is the only thing that costs, and the server, when it communicates, is infinitely fast. But another way of thinking of it, which is completely equivalent, is that the server doesn't exist. And whenever I say communicate to the server, everybody communicates to everybody. Okay? It's like a fully connected network. Because then the server doesn't have to send anything. It doesn't exist. So this result equally applies to fully connected network communication. So if you have fully connected network, you get this for free, and you don't have to worry about server compression. If you do have a parameter server, you have to worry. So it either has to have very fast link to the clients, or you just ignore it, okay, in the mathematics. So you make a huge error in your KAUST model. Okay, so any other question about this? So this will be the first insight. And the second insight is, okay, sometimes you can do even better than this, even in theory. You can get further improvement factors in communication complexity. When can you do that? Well, under additional assumptions. If you know more about these losses. So for instance, if you know that the loss satisfies this inequality, which is generalization of L smoothness, or L1 Li smoothness. Now you don't have a scalar, but you have a matrix, which is positive semi-definite matrix Li. So the scalar case is a special case of this, when Li, this matrix, is a multiple of identity. So this is generalization. And then the question is, if you know this about these losses, can you do better? And it turns out you can design better compressors if you have the knowledge of these matrices. And for linear models, actually, you have that. In neural networks, it's very difficult to come up with such LIs, okay? But we're talking about principles here. So, and in that case, there are some CIs you can design, but you should be compressing this Li pseudo-inverse applied to the gradient and not the gradient. And then you should be taking basically the inverse of this, the product of this just identity of these two. And if you do the design of CI right, and I'm not telling you how you should do it, then it should have this property. Okay, this is a new class of compressors. That was I think the gray one, if I remember correctly. I forgot the color. Then you don't have the standard variance, but you have the variance in Li norm. And here you have a different constant, which is not omega I anymore. Which means that this calligraphic Li generalizes the previous Li and the omega I. So this combines the compression level and the smoothness information. Once you have this, you can prove a similar theorem. For DCGD, which was the original one, which I just showed you before, you get this. Okay, I just copy-pasted the complexity. But for this new method, DCGD plus, which does what you saw on the previous slide, instead of this product, you get this script, calligraphic Li. But this one is always smaller than this. This just comes from the definition. If you look at this, if this is multiple of identity, then this script Li would be that multiple times omega I. But it can be much better than that. So this is always true, which means we cannot lose by doing it this way. But there are many cases where this is much, much smaller than this, even by factors such as square root of n or square root of d or something like this. Huge factors. Could be many degrees of magnitude, depending on the size of d and n. So in these papers, we design such sparsifiers. Not in these papers, where am I? I'm going backwards. In these papers, we design sparsifiers of that type, and here quantizers of that type. Okay. Any questions about this? So here the effect, if you remember the pyramid of effects, I'm not bounding the effect of this away. This is where this trick gives me positive theoretical effect. It improves the communication complexity under this KAUST model. Okay, it's there. I'm not saying this is optimal. I'm not at the top of the pyramid, but the trick is actively helping. And the experiments in the paper showed that this is actively helping. Okay, so here is another type of compression, just to give you yet another type, where you would have unbiasedness, but the variance is not bounded by a multiple of the square norm of the vector that you want to compress, of v. Instead, it's bounded by just a constant. Okay, that's a different class. And And you can run DCGD with this class. And in particular here, this is an integer rounding compressor where what you do is the following. Something like this is very often used in practice. So for instance, it was used in this paper, something almost identical, which is this. You take your vector, multiply by a huge scalar. That's the alpha k. And then the huge scalar, you round to the nearest integer, greedily or randomly, okay? And then you scale it back. Otherwise, you don't get unbiasedness, okay? And use that as the approximation of v. So you can reduce the number of bits that you communicate in this way, because now you only communicate integers, right? You don't have to communicate something big, but only integers. It could be also some small integer formats or whatever. But then you have to do the analysis, and it turns out you can do the analysis. I'm not going to show you now these rates. There are the rates in convex, non-convex case, strongly convex case. You can find all of it there. But the point is, here I want to make a different point. And the point is that in this work where this was first proposed, a constant alpha was used, heuristic large constant alpha. It turns out one can come up with adaptive rules for this alpha k, which have theoretical benefit and practical benefit. You would see here that with these adaptive rules, maybe you don't see it, it's too small, but trust me that the algorithm is much better with this adaptive choice of alpha than the non-adaptive choice of alpha. In any case, this is just an example of yet another property a compressor can have. And now I have one last minute before the break. And this has benefits such as you don't need any error feedback. For, let's say, sine SGD, you need error feedback. There's a famous paper that showed that. For this, you don't need it. It supports all reduce in a native way. This choice of the scaling factors, adaptive actually helps. And you have convergence of all kinds of setups and so on and so forth. OK, so I will take, let's take a break now, and we'll continue with this after the break. So
Perfect, yes.
30 minutes, right?
I think we have about 20, 15. We should be back at 11, just
Okay.
to make sure we give everyone time for